we're going to dive into this topic, building the right architecture for ML and AI at scale. And it's in line with the theme beyond the hype. Okay, so machine learning or AI is really being hyped. And yes, it has to be, because it has so many potential benefits that we think people should be aware of. And in my talk, I want to engage you in some of the architecture that exists for machine learning, the general framework, expose you to some of the applications. You'll see more from other talks. Like I've seen a talk on agriculture and a few others as more. And when you engage with each other, you realize people are doing other things with ML or AI in the industry. And then we'll look at what it means to scale these architectural framework. Okay, so let's get into it. So remember I said machine learning is being hyped because it deserves it, and it can be applied to any area of research or of industry. So let's take the medical industry, for example, where people with issues of the heart or lungs, right? Say you have a pneumonia problem. Usually what you go to, you see the doctor, they ask for an x-ray, and then based on the x-ray, my personal experience, they lift it up to the light and then they check certain things known to them. And then they can tell you that you have pneumonia or some other condition, right? A machine learning model can actually be built using images, a lot of images from patients' x-ray, to be able to determine the presence or absence of pneumonia. Okay, this is one of the things machine learning can do. And in this work from MIT, a group in an AI lab and computer science, they built such a model, a classifier they call it, to predict the presence or absence of pneumonia given the patient x-ray. However, they realized there were so many setbacks to the model they had built. They actually had to build another model they call the deferral model, you see here. And what it does is, when it realizes you can't trust the predictions of the machine learning classifier, then it defers to an expert radiologist to give the prediction, okay? And now the few questions come up. Would they have been able to avoid this deferral model if they had scaled the model or scaled the data set? We'll look into where scaling could have come into the setup and maybe help them skip the deferral model part so that it becomes fully automated, because the purpose of machine learning, in as much as it's not here to replace the work done by humans, it's supposed to be automated and make it easier. So if it has to rely again after being trained on an expert radiologist, then the mission is not achieved. Okay, so let's start off by looking at what ML and AI is. Okay, so I want to put this out there that machine learning is not artificial intelligence. You know, maybe there are some mathematicians here. You could say, no, let's not go with mathematics. Accra is in Ghana, right? But Ghana is not in Accra. And that doesn't make them equal. Ghana can be in Accra. If Ghana were in Accra and Accra were in Ghana, then we could say Ghana is Accra, right? And for that reason, the same reason, machine learning is not artificial intelligence. Artificial intelligence is a very broad field where we want to train systems to mimic the intelligence of humans. So the way we solve problems using our senses, using our experiences and decisions, we want to you learn patterns and then you build your model. In the same way, deep learning, if anyone has been exposed to this term, is not machine learning, because like the premise I gave initially, it is a subset of machine learning where it focuses on using neural networks. When you think of neurons, the way our brain is structured, you have certain connections takes in inputs, gives certain feedback, and it takes certain decisions. That is how the deep learning systems are, and it's just some subset of machine learning. Machine learning is not prone to failure. So there's this hype again that machine learning can never fail, because we, the humans, are the ones who build the algorithms and make the setup and control the decisions that could be made based on what you feed into the system. It is prone to failure. If you give it garbage, it will give you garbage, okay? And then, sorry about that. I think one of them is machine learning is not all about predictions. So mostly you will be told, or you may have been, you may know that machine learning, you build a machine learning model, then you use it to make predictions. I'll have you know that machine learning is descriptive. So given the data set, it will learn the patterns that exist in the data set. And with that, you can actually describe or summarize what you have in the data set. And we'll see an algorithm like this later. It is also prescriptive. Once it has learned the model, learned the patterns, and build the set of rules needed to make predictions, yes, it will make the predictions, but it can also prescribe. This is where inference comes in. So it would look at what it has never seen, okay, and then tell you what can be done or what the output is based on the task at hand. And then there was one that was about not being independent of human interaction. So again, I said, we are the ones who specify the algorithm. You are the one who specify the framework to be used. So it starts off actually with a problem to be solved. You understand your problem, and then you build your setup, your machine learning framework from there. And for that reason, it is solely dependent on us. Okay, so we set it up. In as much as when it's done, it becomes automated. It's all on us. I lost the slide actually. We're working on it. So moving on, I think I may have covered what that is. Now that we know what machine learning is and what it is not, I wish I had can I have my? Okay, so there are multiple stages. Thank you. Multiple stages for machine learning. The current area of research is where we specify an area of problem solving. So you say you want to predict an email being spam or not spam. That is one specific domain that you focus on. And moving on, we are hoping to go into intelligence of machines, where instead of solving just one problem, like we humans are built to do multiple things at the same time, it can also learn multiple things. So instead of just predicting whether something is a spam or not, it can also print what kind of email it is, or how large the email is, and a lot of other things. So computers are smart as humans, but not literally. And then in the future, the ones that are that conscious, okay, so they probably outperform what we do, because they are able to learn so much that we are not able to, the patterns that we cannot see. And this is what raises issues for concern, but hopefully we are not there yet. And there are other areas of research that look at the concerns or issues that arise around all these stages of machine learning. Okay, so for starters, let's look at what classical programming is and machine learning is. Some of us here might be programmers, okay? And initially, say we want to find the mean of all the ages here. As a programmer, what you do is you need to specify the rule for finding the mean, and then you feed it into your system, which is a computer, using a programming language, and then you get results. So once that is done, you can feed in so much data, any amount of data, and then it's like predict. It's always predicts. On the other hand, machine learning has access to the data and has access to the results. And remember, I said it's about learning patterns. It learns the model, okay? So the rules that would have been given to the machine or the computer to compute your mean, for example, is what the machine learning algorithm would learn this time. And afterwards, it might be able to make predictions using what it has learned. And there's always a feedback. So you check how well you're doing, and if there's something you need to do better, you improve upon it. And so that's one thing I want to highlight between classical programming and machine learning. So the machine learning workflow, as I said, it really needs data. So for machine learning, when you think of machine learning, think about data. And for that reason, you can only use machine learning if you have access to data. Depending on the state of the data, you may have another type of algorithm to use, but machine learning is with data. So you start with the input data, and then you have your algorithm. You specify the algorithm. And then the input data is sometimes split into sets. We have the training data, we have the test data. Others might also hold out something they call validation data. And because we want to be able to tell how well the algorithm is doing, what we do is for the training data, we let the algorithm or the model see the training data, learn the patterns, and then make predictions, okay? And then we evaluate, we check whether it is doing the right thing or not based on the set that it hasn't seen, which is the test set. And that's like, this is a simple workflow I want us to keep in mind about machine learning. Now let's dive into the types of machine learning algorithms. There are a whole lot, but mostly they've been categorized into these main four groups: the supervised machine learning, unsupervised, semi-supervised, and reinforcement. So supervised, like the name is, you are telling it what to do. So the data set comes with labels or classes, okay, that the algorithm will see. So if it's an email, it will come with the labels being a spam or not a spam, and that is supervised machine learning algorithm. Whereas unsupervised machine learning algorithm has no access to labels. And for the supervised machine learning problem, you see a lot in examples like linear regression, when you have to forecast sales, or you have to assess risk. If you want to group the performance of customers, say in an insurance company, and you have their labels, like they do so well, or you categorize them as medium, low, or high in terms of the expenditure. You could use support vector machines. These are algorithms that work under supervised learning because of the presence of the labels, okay? And for unsupervised machine learning, what happens is there's the data set, but there's no presence of labels. So for example, when you want to search for something on the internet, and that's the k-means clustering algorithm, there's the k-nearest neighbors as well. What it does, it looks at what you are looking for and looks at the things closest to what you are looking for, and they all pop up, and you have to sieve through them and choose what you want. That is clustering. So it doesn't have the end result of what you want to get or the label of what you want to get, but it's able to use some of these algorithms to suggest or recommend what you could consider. Okay, the semi-supervised learning algorithms are in between the two. So there are times when you have a huge data set, you can't label it all, but you are able to, and we'll see one of the struggles of scalability in terms of the data management. You are able to label some part of them. And semi-supervised learning might be helpful because you can have a smaller set that is labeled, you build your algorithm, and then the bigger set that is labeled can learn using the one that was trained on the ones that were labeled. So it's like it's in between supervised and unsupervised. It starts off with a supervised setup and then transitions into unsupervised setup, whilst keeping the information learned from the supervised setup. And then the reinforcement learning is where an agent has to take certain actions and it's rewarded or punished given an environment. Okay. So these are some of examples. Field learning and model-based value estimation are reinforcement learning, and then the natural language processing naive-based classifier can fall under semi-supervised learning. But as you would see, they are linked together. How would you find, especially for the very huge task you want to solve, you end up using a bit of reinforcement learning and maybe supervised learning, or a bit of unsupervised learning and reinforcement learning. So they work hand in hand. The task you want to solve determines which algorithm you would go for, and that decision you'd have to make, okay, after you leverage certain things like access to resources and all, which would also look at. But these are but a few of the machine learning algorithm. Aside these main 4 ones, there's also the other ones like self-supervised learning, where like the name is, the machine learning algorithm would not have access to any labels at all. It has to learn certain patterns on its own. And once it learns it, so you start off with an unsupervised machine learning setting, it learns patterns on its own, and it uses those patterns to make predictions. And then when it's done, it goes back into the algorithm and try and tweak the performance to make sure it's doing better. So you start off with no labels, train, you learn patterns, and you use those patterns to predict on another part of the data set, and then you feed it back. So it's like a feed forward. It's like a cycle, if I could put it that way, but at some point it stops. So you also determine when it stops. There's the deductive and inductive, and machine learning is both inductive, it is also deductive. Inductive is like you draw a conclusion from, it's called a bottom-up approach. So you have a huge space of validations and then you summarize into something simple, and based on that you can make the decisions. And deductive is the other way around. You need to make specific decisions. Specific decisions. Most machine learning algorithms are hardly one, as I said. And people have proven that machine learning algorithms are both inductive and deductive. One other area that is worth knowing is multitask, and this is evolving, where instead of solving just one problem, say, let's think of something. I think I made an example with a spam email. So instead of just identifying whether an email is spam or not, you can classify in another area. So you have several tasks you want to solve, not just one particular task. I couldn't get a good example, sorry about that. And that is multitask learning. Active learning is also another example. And all these, there are more, but these are like but a few worth knowing about machine learning algorithms. Okay, so before we look at the framework, let's look at how it's being used. This article was written in 2019, I think, and people were looking into how self-driving cars can shape our future. And they are here now. There are some cars that are on the market that are actually self-driving. They can park, they can move certain distances. That's if you are willing to entrust your lives in a car that is driving on its own. But it's mostly based on machine learning, okay? And here we have a lot at play. We have the supervised learning where the model, some part of the model was trained to predict, to see what a traffic light is or what a signboard is. So like it needs to know in terms of the traffic sign. So if it's a stop signboard, the car or the model that the car is running on needs to know that this means stop. That's supervised learning at play. And then we have unsupervised learning where you see the cars. It cannot see all the types and all the makes and all the models and all the colors of the cars, right? So then there's unsupervised learning where given what it has, or maybe semi-supervised, given what it has seen before, it can make predictions that this is a car, you're getting too close to it, there's a danger zone. And this is where reinforcement learning comes in, where the algorithm has to make a decision to stop, right? And not move forward, otherwise it will hit the car. And so yes, indeed, machine learning can be applied to this area, and it's already here. There's another example. When COVID-19 broke out, a lot of people advanced research with machine learning in that area, and Rwanda was also a beneficiary of this. So they launched innovative batch testing with machine learning algorithms. Oh, then there's the problem of protein folding, which was cracked by DeepMind, and it's a 50-year-old problem. So be it biology, be it financial industry, be it academics, anywhere, once you have access to data, and I maintain that premise, you could use machine learning to solve your problem. So we'll see one of the struggles in scaling its data set. And sometimes for those who have already started exploring machine learning algorithms for your specific task, you realize you have to label your data set, right? And labeling your data set in terms of a vision example can be time consuming. So machine learning has come through there as well, where someone developed the V7 lab developed an algorithm. Instead of manually creating the dots yourself and specifying that this is the area you want to consider as an object example, or and give a label in your algorithm. You just select an area and then it does that for you. And that is machine learning at play. The last one is something I have been working on, that is if it's able to come, which is mapping Africa's built environment using satellite imagery. So we pick satellite imagery from certain resources we have available at the office. We label the data sets, and then based on that satellite imagery, we can tell the presence or the absence of a building. And so for those who have been using Google Maps for a while now, maybe 3-4 years back compared to now, you realize that once you zoom in, you see more building polygons, and for some areas, you see more roads. That is the work of machine learning. We are able to build these architectures, learn information from satellite imagery as well. And so those are but a few examples of machine learning. Now let's dive into the machine learning architecture. So just like a saloon car will take you to work or to your fun on Fridays, your TGIFs, and then an 18-seater tractor would carry a lot of merchandise from places to place. Machine learning architectures meet different needs, okay? And we want to look at some of them. The main workflow, so when we talk of architecture, mostly people lean onto the modeling side, but the modeling side is but a subset of the whole workflow, okay? So the whole workflow, I can categorize, and this is not fixed. I can categorize into 3 groups: the data set, the model creation or engineering, and then the deployment stage, okay? So the data set, given the problem you want to solve, you would have to create your data set. So you look for sources, wherever the sources are, you look for them, gather them up, okay. And then you profile the data. So you check the data set to see if there are outliers, if there are mistakes, there are things that you don't want to be there. You take them out, you clean them up, okay, and then you may split them in simple terms. And this is one is I think is the most underrated architecture of the whole workflow. People usually think once I get any data set, it works. Oh, thankfully, a lot of data sets are being created. So there's a lot of sites that has several data sets that can be used for several tasks. If you have access to them, you could start from them, build on what you have. So then you don't have to use a fully supervised setting, but you could use maybe semi-supervised, where you learn patterns from their data set and then build on yours. But this pipeline is very important because, just as I said initially, garbage in, garbage out. If your data set is whack, the machine learning algorithm will learn whack patterns and make whack predictions for you, okay? The next one is the model engineering. So this is where you have to decide, based on the tasks you want to achieve and based on the data set available, does it have labels? Oh, then we go with a supervised setting. Do I want to go deep and use neural networks? Do I have the capacity of a model to build and train it? These are the decisions you make here. When it's done, how am I going to save it? So it is here where you look at your accuracy, you give feedback, you check on your test set to see how well your data set is performing. And that is the model engineering stage of the architectural workflow. Final stage, okay, so before that, let's look at some architectures. You may have heard of neural networks. Neural networks are like the neurons in our brains, okay? So a simple setup will have input and then output. And between the input and output, they are connected by weights. So each input is assigned some weights based on the level of importance or the contribution to what output you're looking at. And then they come together to build, so several millions of those. I had something that should have played, but I think it didn't work. Hopefully in the next presentations, you can see it. But several millions of these come together to make what we call a neural network. And the artificial neural networks are some class of machine learning algorithms. The very common ones are convolutional neural network and recurrent neural networks. The first one, mostly works on images, where you summarize the information. So say you start with a 480 by 480 image, right? You start off with several layers of convolutional neural networks. And what these do is they assign weight at every point to be able to extract the relevant features from your image or from your main data set you're starting with. And then they build upon that to create a certain output, summarized feature, which you could use for prediction or classification. The recurrent neural network, on the other hand, looks at sequences. So the convolutional neural network, the initial one, just focuses on some data sets, which you could train a lot of times. Neural networks actually works with a lot of batches. We'll look at those hopefully too. Recurrent neural network looks at sequences. So for example, instead of training on one image, let's take what I work on, for example, the satellite imagery thing. Instead of working on just a particular year at a particular time, we want to look at 6 years in a row. So 2016 to 2021, for example, you would want to incorporate something that looks at the sequences from time to time. And that is where recurrent neural networks are helpful. And the nice thing about these architectures are that you can combine them. An example of the recurrent neural network is the long short-term memory network, LSTM as we call it. And recently, people have actually combined the convolutional neural network and the LSTM to make a conv LSTM. So then you are summarizing your spatial features into something that is very small. And then you are also looking at the trend as you move forward and backward, depending on what is important to you. Another architecture is the clustering algorithms. And this is k-means at play. So what it does is it specifies, it groups data according to similar features based on centroids. So the X's you see here are centroids for the classes, and it's run through several iterations. And in the end, you can segregate, a better word, you can segregate the whole data set into groups based on these centroids. The K is for the number of centroids. So in this case, I think it's 6. So it's like 6 means. And that's one clustering architecture too. There's GANs, which are generative adversarial network. And what they do is, so the GANs might be different neural networks combined, but the main takeaway is it has two separate networks, the generator and then the discriminator. So what the generator does is, so mostly the whole idea about GANs is you have an image and you want to be able to train an algorithm that can create fake images like what you are feeding into it. Okay. Let me put it simply that way. So the generator is the one that will be working at creating the fake images here. And then the discriminator will look at the real images and say, no, this is real or this is fake. And we have metrics that allows so it's like it's a game of war between the generator and the discriminator network. But once trained, at the end of the training, you realize that your algorithm or your architecture will be able to make predictions like here, where so everything down here are fake, but you would agree with me that they kind of look like some people somewhere in the world, right? We don't know who. So, and this is one use of GANs. So they combine this person with all these people, and based on the patterns learned, based on the connections made, these are the different people that were generated. Yeah. The last one I would want us to look at is autoencoders. So what autoencoders do is it works by reconstructing your inputs, say an image. Okay, so so when I was talking about the architecture of a neural network, this is what it looks like. For example, these two go in as inputs into this one, and this is the output. And these lines you see here are the weights that are assigned into all these inputs. So multiple instances of this combine and make a deep neural network architecture. An autoencoder, first, it has the encoder and then the decoder block. So first, it summarizes all the relevant information. It could start off by adding noise. It feeds it into the encoder, which is some description of a neural network architecture, right? And then once it has summarized all the relevant features from this image that will tell you whether it's a 7 or it's an 8, you can reconstruct it into another 7, a lower dimensional space. And then here is the feedback thing I was talking about, where you measure the output against what it actually is. So you keep giving yourself this feedback until you are able to reconstruct the 7 very well. That's an example of an autoencoder. These are but a few architectures of machine learning. Oh, so this is another autoencoder, but diffusion models that use where it is used for video modeling. So they reduce the dimensionality and then they create all these beautiful images using the diffusion model, which is a variant of an autoencoder. So finally, we could look at the model deployment. So when you are done building your model, maybe the model was not just built for you to make your deductions or your inferences and learn patterns from your data set. It's going to be incorporated into a bigger software. Maybe your company's system is going to use it, or you're going to add it onto a website that measures certain things. This is where the deployment comes in. You'd have to integrate, build, save your model in such a way that you could, so the coding comes in making the decisions. You save your model and integrate it in such a way that it could be used for production. Okay, so if it's something that like someone built a classifier for crop disease detection, and then they were able to deploy it, serialize it into something that works on a mobile phone like an app. Okay, so that's where the model deployment comes in. And then for monitoring and logging, you check whether it's able to make predictions on the new images it hasn't seen, how well it's doing. And then there's another connection here. Usually you give feedback. So this is the whole pipeline. You start off with your data, you create your data set, you clean it up, make sure it's in the best space to be able to learn the patterns from the machine learning algorithm. You do your modeling over here, and then you deploy the model here. Then you go through these feedback. This could take forever sometimes, depending on what you're working on. And that's the machine learning architecture. So I'd also like to highlight these differences. So the architecture is the bigger piece of the design. As we saw, it was from data engineering to model development to model deployment. But when we talk of an ML model, it's just one piece of the model. So one piece of the algorithm trained at a specific instance, which ends certain weight, and then it's like saved to make predictions or make prescriptions. The ML architecture, whilst the ML architecture works at solving, is the approach, the whole approach you specify to solve your problem. The model is a specific instance trained on your data set. And then the whole architecture comprises of several working parameters, but the model is made up of weights that are already trained and can be used to make predictions. Okay, how am I doing time? Good, I hope. Okay, so finally, what we want to look at is the scalability aspect of ML. We've learned that you build your data set, you create your model, and then you deploy it. Scalability comes in if you can get a bigger size. So, and it depends on the task you want to solve. Some of the tasks or the domains of problems require that the size is as huge as possible, okay? And given your time constraints, you wouldn't want to spend like 3 or 4 months just training one particular model. So the speed and then the complexity, how it's able to learn from the data set, the patterns from the data set that you feed it into. So when you think of scalability, think about the size, the speed, and the complexity of your ML framework, not just the model, okay? And what this does is it helps in productivity. Imagine training a model. So Kofi, on the other hand, doesn't have access or knowledge about how they can scale their ML model. So they use whatever resources is available, not knowing the availability of others to them. They could take like 5 days to train a model, whereas you check on Kweku, and Kweku just use probably a day or two to train the same model. So it increases productivity. And then you could save it in ways that could be shared. It reduces costs. It also minimizes human effort. These are some of the benefits of scalability. Let's review the ML architectural workflow. So you first need to understand the domain of the problem you're trying to solve. And based on that, you make definitions about the data sets you're going to collect, where you're going to collect them from. You clean them, you wrap them up, you split them into your training, test, and maybe validation. You make specifications for the model you want to use. You train your model, you evaluate, and then you deploy your model. This is like the whole process of the ML framework. However, each of these stages has issues with scalability. When it comes to the data handling, we say I think it makes sense to say that because the machine learning algorithm learns patterns from the data sets, the bigger the data sets, the more the patterns learned, right? Like we even have, and this might be biased, but some people say the experience is the best teacher. So you will learn better from more experiences, from more examples, okay? And so for that reason, machine learning has an issue with the data set. If your data set is not large enough, depending on the algorithm or the architecture you want to use, you may not be able to learn the right patterns, and you may not be able to use it to make the kind of predictions or prescriptions you want to. So it will fail for you because of the bad data set, right? So the scaling challenge starts from here, the data set. And even understanding the problem and how you're going to solve it could be an issue. When you collect the data set, imagine you're able to get millions of data sets, and you are like a group of 5 people starting an ML company. How are you going to house the data set? Where are you going to keep it? Do you have that much storage space? There are big companies like Google, Microsoft, Apple, Facebook. They are making some of these houses available where you can buy depending on the size. Like there's a threshold which you could use for free, and after a certain threshold, you have to pay for it because you're using it for your own needs. And all these are challenges people face. And then during the training, you have to decide on which model you're going to use. When you're training, like I said, Kweku would use maybe just the CPU and then would train for several days. Whereas Kofi knows about tensor processing units and GPUs and can parallelize the training of the model and train faster. The evaluation is also a problem. People tend to think about accuracy when we talk about model evaluation, but sometimes you may have to develop a new evaluation metric, not one that exists. So you pick 2 or 3 metrics that are already there. Evaluation here is where you tell how well the model you are training is doing based on the predictions it's making. So for the evaluation, you have to be able to scale it up according to your data set and the model, and then the deployment as well. And all these stages face scaling challenges. Let's briefly look at how we could address these. So I would, based on these blocks, I would categorize scalability of ML into these 3 main stages. So you first prepare, you build, and then you deploy. So for preparation, you have to decide on the language. Let's start with the language. We may be aware of JavaScript, C++, and Python. When it comes to ML, most people tend to lean to Python, okay? And most of these Python libraries or frameworks are actually wrappers around C++, okay? JavaScript is known to be slower. and I'm not sure if it's debatable. Some people are able to find a work around that, but it's not being able to get to a point where you could fully use that to build an ML pipeline or framework without having any setbacks. So you need to decide what the framework you're going to use. And language. So the language is the programming language. The right framework, there are for ML libraries, there are ones like Keras, there's ones like TensorFlow, there's ones like PyTorch, Scikit-learn. You may need 2 or more of those. You need to find out where they are, how to access them, and then probably take some starter courses. That's if you've never used them before. So all these are decisions you have to make. The right processors. So I mentioned the CPU and then the GPU and then the tensor processing unit. I think I could highlight the difference between the three as this. When you want a place where you want to store or run, okay, so during your model training, if you're thinking of where you could do things like flipping your data set, if it's an image data, you don't want it to look, if it's an image data of identifying dogs, right? And you realize that they are not flipped. Once it goes out into the real world and it sees a flipped dog, your machine learning algorithm may fail, right? So you have to augment it with flips of the images. You could do all these and save them on the CPU. The GPU is a higher version of the CPU, the graphical processing unit, and it's mostly good for vector operations. But the thing about the TPUs is we spoke about the neural networks, how they learn weight and how they are connected to each other. These weights learn can be organized as matrices. And so then the whole neural network architecture, it starts off by wanting to find a solution to your problem using a function approximation, okay? So you want to learn a function that can give you solutions to your problem. And then the function is made up of addition and multiplication of matrices. And these work well with the tensor processing unit, and also the graphical processing unit. So you need to identify where you could have access to these right processes to scale up the speed of your training procedure, okay? And then also for the storage of your data sets, the input pipeline is another thing that you could decide on how to scale. Maybe you would want to go deeper with your neural network and how the output will look like. All these are different areas you could decide about how to scale the pipeline. The distribution comes in when you try to use the model parallel. I think you guys know the word I want to use. Thank you for being understanding. So yeah, when we look at distributed ML, it has to do with the data set and the training as well. It falls under the data set and it also falls under the training, where given the processes you use, you could do multiple things at the same time. So it's like divide and conquer, yes. So you want to learn patterns from the data set. Your neural architecture network is very deep and big, and each of the parts of the neural network are doing their computations using different TPUs, for example. So you do this parallelism. Yes, I think I got it. And then at the end of the training, when everything is learned, they come back together and then give you your final output. Oh, and then one thing you also have to do is you have to monitor your resources and how you utilize them. And then the deployment stage as well. So another thing is, aside the whole, and this has to do with the pipeline of ML framework, okay? So at every stage, there's something you could do. There's some decisions you could make that could scale up the performance, the complexity. Sometimes it's like a cost and accuracy thing. So the more costly it is, the less costly it becomes for you. If you are not able to scale enough, depending on the problem you want to solve, then you'd have to pay the price of losing some form of accuracy of the ML model, the patterns the ML model has learned. However, there's another evolution in the area of machine learning or artificial intelligence where people are trying to be multimodal, where instead of focusing on one data set to learn certain patterns and make predictions, they look at multiple data sets. So instead of just images, they look at speech as well, or text. And then instead of making predictions on only images, they do multitasking where they try to do several tasks at the same time. Okay. And then people are also working on you saw how the picture of the neural network was. It has so many connections. It could get so dense. And sometimes not all that is learned there is useful. That's one problem of deep learning. So people are leaning towards building sparse networks. So not everything, not every neuron that was there is learning something. You make some, like you deactivate some of them. There's a technique for doing that. And then the ones that are relevant to you, they learn the information, and eventually you can save your model, build your model, and make your predictions. But is AI just the best? So there once scalability comes in, then people get worried about the fact that AI might not be responsible or it's not private. But all these areas listed here are active research areas in artificial intelligence, where people are trying to make sure that we can build models that are explainable, fair and not biased, respect the privacy of others, and ethical. There's actually a set of principles for the ML algorithms or ML models used, and you would have to make sure you follow that once you decide to use AI or ML. So I'll end here by saying that in order to build a scalable machine learning model, you need to understand your problem domain, because with that, you could build on the other areas of the pipeline or framework of your ML architecture. And if you have access to data, then ML or AI may be useful. I say may because not in as much as we are hyping ML and AI, we are saying it solves problems. Not all problems can really be solved. We are not there yet. Not all problems can be solved by ML and AI. The cleaner the data, the better the patterns learned. And if you are not able to scale at any of the stages, people are working. So the big companies that have access to all these resources like Google, Microsoft, Facebook, and the rest, they do a lot of work by building models and deploying them or sharing them out there. So you can pick these models, fine-tune them, and start from there. Thank you.
Thank you very much, Abigail. So for now, it's time for questions. The microphone is around. If you have any questions, you can just raise your hand. And any questions?
Good morning.
Good morning.
Julius is my name. Abigail, thanks for the presentation. You mentioned that, and as we all know, garbage in, garbage out. So if I have WAC data set, but I diligently work on the model, I don't think it should give me WAC results because.
So yes, thank you for the correction. Maybe WAC is too strong a use of a word. It won't give you results as good as the result will not be as good as it would be if your data set was also cleaner. So the more you are able to scale at every stage, the better the results your algorithm can learn. So if you focus on the modeling, some data sets are that bad, like the complexities are so much that no matter how well you build your model, right, because the complexities in the data set are bad, it can't just identify the patterns because there are others there that are messing the model up. So you spend a lot of time building your model, right? And then when you are done, your bad data set will just kill all that effort. So if it should have been 20% or 30% gain, you just get a 1% gain. And other times you don't even see the effect at all.
Okay, because I'm just tempted to say maybe you get good WAC results as well?
Yes, you are allowed to say that, but if we're going to spend time building a model, looking for resources, then we should get the best out of it,
Sure.
right?
I agree.
Hello. From the summary of your presentation, the first thing was having domain knowledge, understanding the question. Does that mean that if I want to enter, like, let's say, the medical field of data science, I should be able to have knowledge like a doctor before I can work there?
Then there's this thing about teamwork, right? So if you're able to make the right connections with the people that you need, so you would need a software engineer, you may need a data scientist to focus on the data set, though at some points the engineers kind of become good at all the stages. You could also get the technical people on the board, and there are systems like that. I think there's Google Health that actually works with doctors and clinicians on the ground. So they do a lot of those technicalities that are not entirely ML, so that you take that load off yourself. So if you are able to reach out to people who can help with that, if not, then it becomes all you. And sometimes just a meeting or two, once or two times, they can clarify certain assumptions you are making, certain things you should look out for, and that should be enough. And that's where their input comes in.
Okay, mine will be quick. So Abigail, I think you've been practicing here and doing a lot of research here. What did you see to be the biggest problem in solving domestic problems here? So problems in Ghana here with machine learning, especially you working with Google. Can you highlight some of the challenges that you've seen so far?
So the first challenge might be the fact that the awareness is not enough, right? And people are not aware of the use of this tool we call AI or machine learning and how it can benefit them. And then having access to the right support at every stage. So if it's the data set, where do I go to get the data set? There's so much, I don't use the word protocol, but there's so much things you need to go through sometimes. If you're creating your own data set here in Ghana, imagine you have to go through the ministries, you write a letter, you see this person, you see that, it kind of discourages you, okay? Those are like the two main challenges I can think of. Getting access to it, because the ML models are there. There's the swarm of internet. We have access to so much, but building the data set, the right data set to make these research worthwhile is where the main challenge starts from. And once we get there, I'm sure we could make progress with ML and research.
So you've made a lot of emphasis on the data, okay? And that garbage in, garbage out. And that part is part of the data engineering process. From your side and how you've been working so far, are you the one who handles that section, or you have a data engineer who does that? And what has been your relationship with the data engineers, if they are there, and what would you advise with regards to machine learning? Because it's not something that is talked about very often. So yeah, just give me your point of view.
Your questions were in threefold. If I handle these things myself, no. So we have a group of people we call the annotators. We send them the data set, like the one that was automated, where they use the right tools and then they label the images and then they check. But we come in by validating the data set. So we look at the data set, we know the model we want to build, we know what we are trying to solve, right? So we check and see, for example, this thing about the satellite imagery for checking buildings. Then we see that they selected, say, a bus, for example, as a building. Then we'll have to give them that feedback. And then they run all the analysis and we keep going back and forth. So we don't handle everything. We just go to those with the right skill set to support the team to do what has to be done. And it's everywhere. Okay. Data science is actually, some say it's a subset of machine learning, but it's debatable. I think they meet each other at some point. Okay. The thing about ML is AI is the bigger picture. Okay. And ML uses algorithms to learn patterns to make solutions. And it's automated. So it's such that once you learn a certain pattern, if you put in your effort, train your model so well, get your data set, you can always go back to it wherever you ended from, tweak it and use it for something else. Okay. So it's a field that I feel like every industry should explore if possible. Remember, I said it may not be useful. And the sad thing is, if effort is not put into getting the right data sets, then most of the time you don't see the real impact of ML. So you may make good work predictions. Thank you for that. But it won't be the best. And if you're going to make information, say an insurance company needs to make information based on this, I think good work is not enough, right? So it is an emerging field. People are using it all over, and it's something that it could be explored. So if you could get a team that wants to focus on that and explore the methods from there that could be helpful for your industry or for your group, it's something worthwhile trying. And then as you do so, you could liaise with experts in the field. So you could make use of Twitter, for example. You see one ML engineer who is always tweeting about something, reach out to this person that I want to work on this. What is your take? You meet them, you discuss LinkedIn and all. So you connect with the community, make use of their skill sets, the human resource, and then you feed that into what you're trying to do, and then you build up from there. Eventually, at some point, you would realize ML is not for me and you will stop, or you realize it's the thing for me and you keep going. But at least it was worth trying, knowing that, oh, I also tried that. It didn't even really work for me, maybe because of this. I hope I answered your question.
Okay, I want to find out, I think you made mention of domain knowledge. Okay, but I was expecting to hear something like the first aspect of the process, like talking about problem definition, because most of times data science problems are defined in like from business perspective or society perspective. So what I want to find out from you is, if a problem is thrown to you, like, okay, we want you to predict so and so, how do you translate that into a data problem?
If a problem is thrown to me,
Yeah.
how do I transform that?
So maybe design maybe a model that will predict maybe sales of goods or so and so. Yeah, so like I was expecting to hear something like, okay, you translate that into a data problem, because the problem, the question is like they are looking at business perspective. Yeah, so design a model that will predict maybe sales of a particular good or something. So what I want to know is how do you translate that into a data problem?
I think I'm not sure what the data problem is, but let me take a chance at this. So yes, you were right. Maybe I may have said it at the beginning, and that's why I missed it at the last, but you need to know the problem you are trying to solve. And I may have said a few times that machine learning is helping with problem solving, right? Socially, academically, in every industry. So once your problem is defined and you understand the domain of the problem, right? Then for machine learning, you can make it a data problem if you realize you can generate the right amount of data to learn the patterns that you want to learn. Does that answer your question?
Yeah, partly.
I got two parties. So it's more like the thing about ML is it feeds on data, and like that's why I've been hammering the data part. Your data set has to be good. If the data problem is how to get the data, is that what the data problem is?
I got this from somewhere where it stated that most at times that the challenge maybe that the challenge students face when they are to maybe take part in an interview, because at the end of the day, your employer is expecting that they will actually give you a problem, maybe in the maybe a business problem. So they want you to see how you can translate that into a data problem. Because if you are not able to translate the business problem into a data problem, solving it will become a problem. Because at the end of the day, okay, yeah.
Yeah, I just want to, for the interest of time, so Abigail is in Google Research, right? So she does a lot of research. I work with business people, so I know what you're saying, but it all starts with understanding the business, which is the domain that she mentioned, that you have to know the domain, right? So if it's retail and you want to solve a retail problem, you have to know the domain. But after you know the domain, you have to understand the operations of the domain. So if it's a retail, how is data being captured? So people come to the store and they buy something, right? Do we have all of that data? What is the problem that you want to solve? Is it more of supply chain? Is it more of customer retention? If you understand that, then you need to think about the data points that is being collected for about that problem. And once you know that, you can actually think. So before you come to the algorithm, there's a lot of thinking of the problem that you need to do, right? And so if you want to talk about that more, a lot of us will be gathering around in the course of the event, and we can discuss that more as well. So
Makes it gives clarity. I think it could also fall under feature engineering. The features of the data set are those that are important for the patterns you want to learn and what you want to predict, which he rightly said in your own terms. So that is feature engineering, and it's actually a stage of the ML workflow where you have to decide which features you want to keep, which features contribute more to the problem you're trying to solve. So yeah, maybe then that is how the problem is. We could talk afterwards, I guess. Thank you.
One last question from online, and the person is asking, what is your favorite architecture, scalability, and why?
I can't pick one because they come hand in hand. I won't want to limit myself to what each of the other ones benefits, the benefits they give. So I don't have a favorite. Yes, but if possible, well, for me, because of where I am and the group I work with, we have access to so much resources. So scaling is sometimes, most of the time, very easy to do, right? And maybe that is why I don't have a favorite. But yeah, if you are able to get all these in place, then it helps. Thank you all. Yes, I'll make the slides available too. Thank you.